All right, I want to go through an important example that I didn't have time to do in class today. So this example is conservation of linear momentum applied to a converging nozzle. So the idea is that I have some, nozzle that concentrates a flow down to a faster velocity, right? So that the exit velocity is higher than the velocity at, let's say, the inlet to the nozzle. So I'll call this like V exit. It's got its own cross-sectional area, and then at the entrance, or I shouldn't use entrance, I'll call it, there's some other inlet area and some different velocity associated with that I don't necessarily know ahead of time, but I can figure it out by mass conservation. So like typically you would know, let's say, the volumetric flow rate at the exit, and you could back calculate this. So we'll do that as part of this problem. But the important bit in this problem is the pressure effect. So, let's just think about this for a second. So if I'm thinking about conservation of linear momentum, I have relatively slow moving liquid that came in, and very fast moving liquid leaving. If I didn't know any better, I'd say that this had actually gained some linear momentum. So I don't know, I guess that mathematically would require me to apply some force to the fluid to move it. But in practice, you guys, I don't know, my intuition is that if I have a nozzle, if I want the nozzle to not fly away, I actually need to provide a reaction force that moves in the backwards direction to keep the nozzle from flying away. So what's going on here? Well, your intuition is right. You really do need a reaction force that moves in the backward direction. And the reason is that there is actually a pressure that builds up on this face here. So according to Bernoulli's equation, if I have fast-moving stuff here and slow-moving stuff here, that means, so this is slow-moving stuff, so that means the pressure, so the velocity is lower, so the pressure is higher in that location. So part of our conservation of linear momentum is going to be including these pressure forces in our analysis. So let's go through that. So I'm going to create a control volume here that just kind of goes around my nozzle. I won't worry too much about how this reaction force is connected to this nozzle. In practice, there's usually a screw or maybe some threading here that's absorbing that through the boundary. But the idea is that there's some reaction force that acts inside this control volume on the fluid. So how does that happen? Well, first let's go through, let's say, Bernoulli's equation here. Well, actually, let's start with mass conservation. So mass conservation would say that the volumetric flow rate, or if the density is a constant, then the volumetric flow rate would also be a constant in here. Right, so rho V in A in is equal to rho VE AE. So obviously these two things are constant, and these things are known. So you can solve for, let's say, the inlet velocity just in terms of the exit exit conditions, right? So boom, that's conservation of mass. Conservation of linear, we'll use Bernoulli's equation next, right? So Bernoulli's equation will help us figure out what the value of this pressure is. So that would say that, for example, the inlet pressure is tied to the outlet pressure, or the exit pressure, by the velocities. So in this case, actually, you can probably see I've already not written the change in height here. You could think about that a couple of ways, but I guess I'll take this streamline right here where nothing actually changes. Alternatively, it probably applies for these two if the changes in height are relatively small. But I'll neglect the gravity portion, the rho g times z portion, Also, the exit is at atmospheric pressure, so I'm going to work in gauge units. So the pressure is 0 at the exit, and then that allows me to find that the pressure at the inlet is just half rho times the difference in velocities. You can use mass conservation to eliminate this if you wish, but at this point I'll just leave it the way it is. The important bit comes when we go to apply conservation of linear momentum. So if we write out conservation of linear momentum, it says that some of the external forces is, some stuff that involves a volumetric integral, which we won't actually have to do. Which we won't actually have to do because we have a fixed control volume, a steady flow with a fixed control volume. But another term that involves the inlets and outlets, right? Rho times V dot N dA. And again, like our control volume is fixed, so I'm not even going to bother to write the relative velocity here. This is just the velocity of our fluid, dotted with the outward facing unit normal. We'll integrate that over our control surface. The important bit, the new bit in this problem, is that if I come up here and look at like the outside of my control volume, there is an external force at the faces that has to do with pressure. So in addition to the fact that we have a reaction force, that's this thing, so we've got some reaction force which represents, like, let's say our threads that have to hold this nozzle in place. There's also a pressure at the inlet acting over area AN, and in principle there's also one at the exit acting over area, let's say, A out. But in fact, like I said, like we're going to work in gauge units where this one's 0, but this one's not 0 in this case. It's actually a pretty large number. So we'll do that. Let's see. And then we've got a couple other terms here. So these are we've got to keep these terms around. So we have an inlet over here and an outlet over here. So we need 2 terms for those. So these are my inlet and our exit. So that would be rho times, so this thing will be in the positive V, like the positive direction. So I'll call that V in. And then this is a scalar, right? So this represents the velocity dotted with the unit normal. So the velocity goes this way, but the unit normal is going this way, so they're in opposite directions. So this term is a minus V in times the area at the inlet. So that's our inlet term, and then there's an exit term as well. So that would be plus rho V exit, right? Positive V exit because flow's going this way. And then the V dot N term, so in this case V is going this way, but the outward facing unit normal here is going in the same direction. So that's a positive VE A exit. And that's pretty much it. Then you just put it together. I'll move some signs around here. So since I want this thing to have a positive sign, I'm going to move this to the other side, and then I'll move these other things to the other side of the equation. So in the end, we'll get Rx, our reaction force, is Pn times An plus rho Vn squared An minus rho Ve squared Ae. I think I might break this video and actually turn these into some numbers for you to see that often it turns out that these terms are bigger than these other terms. So, but let's go ahead and like plug in some numbers to check that out. But this is our boxed answer for the amount of reaction force needed. All right, so let's take the work that we've done on paper and put some numbers to it, just for the sake of doing comparing the size of some of these terms. So here's the idea. So our paper results went something like this. So we found that using mass conservation, we could find the inlet velocity in terms of the exit velocity and the two areas involved. Bernoulli's equation allowed us to connect the inlet pressure to the change in velocities that had to occur due to mass conservation. So that gave us our half rho v squared at the exit minus the v squared at the inlet. And then our total force that had to act on the nozzle had a first term that had to do with pressure acting on the leftward side of the of the fluid at the inlet, and then there were other terms associated with momentum flowing into and out of the control volume. So what the point of me doing some numbers here is mostly just to compare the relative size of these. Okay, so I chose a couple of example parameters here. Like obviously the numbers depend on the physical situation. For example, let's use an exit velocity of like 10 meters a second, which is a pretty high speed flow. A density of 1,000, so that's water. And a relative area, so like the exit areas maybe corresponds to a 1-inch diameter, and the inlet would correspond to like a 2-inch diameter. So that would be a pretty big reduction in area. That's like a fourfold reduction in area. Maybe I should use 25 here for an inch. All right, and then we'll evaluate. So I just used the three equations that we got. The one thing that I'll do here is I'm going to break our terms out. So there was a pressure term, an inlet momentum term, and an outlet momentum term used to calculate the total reaction force required to hold the nozzle in place. So I had defined this number to be a positive number if it pointed to the left. And I have kept the signs of these so that I can compare the relative size. And then I'll just export them. So evaluate, evaluate, evaluate. 1, 2, 3, 4. So what you'll see is that the inlet pressure is a good 45 kilopascal or 47 kilopascals higher than at the inlet when you evaluate, which is a pretty large pressure. That's like more than half an atmosphere, or almost half an atmosphere anyway. So when you go to compare the three terms that show up in the reaction force, what you'll find is that the pressure force is actually by far the biggest force involved. And there is an outlet, like these other terms do exist, right? Like, so there is an inlet rate of momentum flowing into the control volume, and there is momentum flowing out of the control volume, but overall the pressure term is quite important to determine the final force. And if you don't include it, you'll get a grossly wrong answer. And in fact, if you don't include this term, the sum of these two, like which doesn't include the pressure force, will actually point in the wrong direction. I think some of you have discovered on the homework there is a problem like this. I don't remember what the problem number is that involves like a little cone at the exit of a nozzle. If you don't use Bernoulli's to calculate the pressure and then use the pressure to calculate the sum of the external forces, then you'll actually get the wrong sign for the amount of force required to hold the cone in place on your homework. So keep in mind this is an important thing to do. Okay, so that's a good starter problem for using pressure as part of your external forces.